Okay, so you lay down 6 carbons because it's hexane. Number the carbons left to right, right to left, doesn't matter. Just number them however you want. I just go left to right. And then just hang off the functional groups or the non-hydrogen groups according to what's in front of the longest carbon chain name. And the number in front of methyl tells you it's a CH3, which is methyl, hanging off of carbon number 2. So the number 2 tells you which carbon it's attached to. The number 3 tells you that that's where the chlorine is attached. That's it, right? Now, what if I wanted to do this as a condensed structural formula? How would I write that? What would carbon number 1 look like? It'd be a CH3. Carbon number 2 only has how many hydrogens? Carbon number 2 has 1 hydrogen attached. Do you see that? Okay, so that would be a CH, and then coming down is a CH3. That's the methyl group. Then carbon number 3 has how many hydrogens? Just 1. And then hanging off of it is a chlorine, and it could be sticking up or down. I'm just sticking one up, one down, just to make them sort of stand out a little bit more. It would be fine if you stuck them both pointing down. Then what does carbon number 4 have? CH2. Carbon number 5, CH2. And carbon number 6, CH3. Okay, so do you see going along? If you wanted to do it as, you could do it as a complete Lewis structure. You could do it as that's a condensed structural formula. You could also do this as a zigzag. If I was going to do hexane as a skeletal structure, how many lines? 5, right? Remember, if hexane is 6 carbons, so there's always 1 less line in your zigzag. So this would be 1, 2, 3, 4, 5. And if you count 1, 2, 3, 4, 5, 6, like count each corner and every end, you should see 6. So then where would I put the methyl? The first corner going up, that's a methyl group, right? So just the line sticking up is a methyl. And then how would I put the chlorine? The next one coming down, and the Cl. Okay, so any of those, these are just 3 different ways of drawing that molecule, but just follow these steps. Okay, so always look at the last name first. It's hexane. Tells me to put 6 carbons in a row. Step 2, just number the hexanes. Number them carbon 1, carbon 2, 3, 4, 5, and 6. Then 3, add the hanging groups. 2, based on the number in front of the group. Methyl goes on carbon 2. Chlorine goes on carbon 3. You don't have to worry about the alphabetical order. You don't have to worry about any of those. Just remember that if you have a Lewis structure, anything above or below, left or right that's not a hanging group is a hydrogen. If you do a condensed structural formula, the hydrogens you write after each carbon is how many are directly attached to the carbon. It's the easiest, I feel, if you then drop your non-hydrogen groups above or below the carbon they're attached to, sort of like I did in this one, right? So see the CH3 hangs down, the chlorine sticks up, but it would be fine if you hung them both down. I was just trying to make it so that you could tell they're not attached, that they're on their specific carbons. And then if you do a zigzag, remember you start with the long chain, however many carbons in that chain, you're going to have 1 less line. So there's 5 lines in my zigzag. Then I have a methyl off of the second corner, and then a chlorine off of the third. Okay, so see if you can do this one. So this is decane, which means how many are you going to draw? 10. Okay, so the first thing you always look at, number 1, look at the very last word. Decane is 10 carbons. That means you're putting 10 carbons in a row. If you're going to draw a Lewis structure, remember, this is where the fun comes. Carbons are going to have a dash above, a dash below, and then a dash on either end. So now the next thing, what are you going to do? Number them. Which is also a good way to check and make sure you put enough carbons down, right? Because the number should match whatever the name was. So you see 10 carbons numbered 1 through 10. Third, add the hanging groups. So if it's 3,4-difluoro, what am I going to put? I'm going to put a fluorine on carbon 3 and a fluorine on 4. It would be fine if you put them both here. It'd be fine if you stuck them both off the top of carbon 3 and carbon 4. You could do 1 and 1, just so long as there is a fluorine stuck onto carbon 3 and a fluorine stuck onto carbon 4. It doesn't matter. The above and below part does not matter. And if you remember back to lab, these rotate. Okay, so these molecules are not like rigid and stuck. They have the ability to flip about, so either one would be fine. So I'm not quite done. I now have 7 ethyl, so what do I have to put? I have to put a CH2, CH3 hanging off of carbon 7. And it could stick up or down. It doesn't matter, just so long it's on carbon 7. The 7 in front of ethyl tells you where the ethyl group goes on your longest carbon chain. So that's it. I took care of 3,4-difluoro, 2 fluorines, 1 on carbon 3, 1 on carbon 4. Took care of 7-ethyl, which is a 2-carbon group hanging off of carbon 7. See all those empty dashes? Those are all what? Hydrogens. Jeez. Carbon's got 4 covalent bonds, so remember that. They will always be like a dash above, below, and on each end of a chain. So now if I want to do the condensed structural formula, carbon 1 would be what? CH3. What about carbon 2? CH2. Carbon 3 has how many hydrogens? 1. So it's a CH, and then F is hanging down. Does everybody see that? Okay. Going from like a Lewis structure to that condensed structure. How about carbon 4? It's also a CH with a fluorine hanging off. Carbon 5, CH2. Carbon 6, carbon 7. And then hanging off is a so a CH2, CH3 hanging off, that is an ethyl. 8, 9, and 10. CH3. So everybody sees where, so every time when you're looking at a condensed structural formula, that carbon, the number of hydrogens next tells you how many are attached to that carbon. Now, what would I do if I wanted to do the skeletal structure? How many in my zigzag? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. See how fast that was? Okay. And so then hang a fluorine off of 3. Now remember, where do you start your counting? On the very end, right? So that's carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So remember, every end and every corner is a carbon when you do your chain. So hanging off of carbon 3, I'm going to put an F, and off of 4, F, and then off of 7, what is 7 going to look like? A line and another line, like a line with a bend, right? So 7 is going to come down and go like this. Right? So you see that that is a CH2 and that end would be the CH3. So a single methyl is just like, looks like a stick coming off of your skeletal line. But an ethyl would actually be a line and then a corner in another line. Okay? All right, so we'll do these top 2. We'll leave that last one for next time. So 3-ethyl hexane. This one pretty quick. What do you put? Three-ethyl hexane. 6 carbons, right? Look at the last 1, 2, 3, 4, 5, 6. Remember, that means line up, down, and then on the ends. So you can number 1, 2, 3, 4, 5, 6, but what am I going to put off of carbon 3? Bless you. Hanging off of carbon number 3, you're going to put a CH2, CH3. That's it. All the rest of these dashes have hydrogens, right? Because carbon's got to have 4 covalent bonds. So those, you don't end up having to add them into the name. That is sort of assumed they are there because carbon has to have 4 covalent bonds in order to be stable. So there is hydrogens above, hydrogens below, hydrogens on either end, except where there's a non-hydrogen group hanging off. Changing this to the skeletal structure, how many zigzags? 5. 1, 2, 3, 4, 5. Boom. Okay, and then as you go counting, count from the starting at the end, 1, 2, 3, coming off of carbon 3, a line and a corner. So that's an ethyl. Okay, so some people really like the skeletal structures. Just make sure that you go back and like count them. And I don't care if you add back dots or things like that as you count your carbons to make sure you see them. What about 1-bromo-3-iodocyclopentane? What makes this different? It's a ring because you see cyclo. So now it's not just pentane. If you see cyclo, then you know it's a pentane, but it's cyclo, which means I need to make a ring of 5, right? So the name tells me how many carbons, but when you see cyclo, automatically you know you've got to make a ring structure. So this is 5 carbons in a ring. Each of those carbons would have how many other bonds? 2, right? Because remember, they've all got to have 4. Carbon's got to have 4 covalent bonds. So you could go back and add all of those. So whatever's not a hanging group or a non-hydrogen group ends up being a hydrogen. So now, 1-bromo. How do I know? How do I number this one? What's the rule for this? You can number it any way you want. Okay, just number it in a either clockwise, counterclockwise, pick a spot. Doesn't matter. You could be sort of like a clock and always start at the top, but it really doesn't matter. I'll start over here. So 1, 2, 3, 4, 5. Just number the carbons in the ring. When there's a ring, that becomes like your longest carbon group. So now I know where I put my bromo would be on carbon number 1. And then I'm going to put the iodo, which is iodine, on carbon number 3. All those other dashes are what? Hydrogens, right? So that means that carbon 5 has 2, 4 has 2, carbon 2 has 2 hydrogens. Carbon 1 and 3 only have 1 each. Do you see that now all those carbons, everyone has 4? Skeletal structure is going to look like the little house, right? So just make sure there's 4 corners in your ring. 5 corners, sorry. 5 corners in your ring. Again, doesn't matter which way that you number them. You can number them any way you want. I could number 1, 2, 3, 4, 5. I could number it clockwise, counterclockwise. Pick any place to start with your 1. Really doesn't matter because you could flip this around. Carbon number 1, though, is wherever you number carbon 1, that's where your bromine goes. Wherever you number carbon number 3, that's where your iodine goes. And that's it. So it doesn't show any carbons. It doesn't show any hydrogens. Skeletal structures only show the halogens for us, because we're not going to name anything else. The only thing you would actually have an atom on would be the line going to like the bromine and the line going to the iodine. Those are the bonds to those halogens. Okay, so I will leave this one. So in your homework, chapter 4. So in chapter 4, maybe you struggled and got through all of the homework. This is the post-lecture homework. Remember, the post-lecture homework is assigned. There were actually 18 points in chapter 4's post-lecture homework. I counted the first 6 when I did your mastering assignments for exam 2. So you may look at your exam 2 mastering numbers and they might be really high because maybe you did more than 6 of them. Okay, so as long as you got at least 6 points out of 18 in chapter 4, then you got credit for that part of the assignment. That assignment is now still open, and so questions 7 through 18 are what we're covering now. So you should be able to then answer this for exam 3. Okay, so if maybe you didn't do chapter 4, you still have the option of going back and doing this one. Okay, if you did do it, well, then it's already going to show that it's done. So you're all set. Okay, so you can go back and look at it. But so this is really like questions 7 through 18, which is 12 points. This is going to go on to exam 3. Okay, so it's open so that you could go ahead and do those. This has things like drawing when you're naming. I had some students who were like really challenged with the chem draw. Don't know if you've tried that or not. The chem draw, it looks like a little pad, and you've got atoms, you've got bonds. Here's the steps. First thing you do is you put down all the atoms that you want in your molecule. Okay? You put down like every carbon, every hydrogen, put them on the pad where you want them. The second step is you switch to the bond. So the bond looks like just a dash. Okay, click on the bond. Then when you hover over an atom, it'll kind of turn blue. You click on it and drag to the one you want to link it to, and that'll form a bond. So you just click it and drag, and you form a bond, and you click it and drag. Put all your atoms down first. It says that in the instructions, but somehow that gets lost in translation because it seems like they try to tell you way too much stuff. So that's the order. Put all the atoms down on the little pad. So like pick your carbon, put your carbons where you want them. Pick your hydrogens, put your hydrogens where you want them. Pick whatever they have you try to do. Then go through and click on the single bond, just the single dash. Hover over an atom, click and drag, and that'll make a bond. If you have to add non-bonding electrons, like one of them wanted you to go back and add the dots that weren't part of the bonds, do those last. Okay, do that last. If there's any that had a charge, do that absolutely last. Okay, so put down the atoms, form the bonds, then do any non-bonding electrons if it tells you to. Okay, so that's like just sort of the steps. You'll find that, because if you try to do the bonds at the same time, you start laying carbons everywhere. Like every time you click, it starts putting more carbons, and you're like, I don't want that one. Wait, this one's here. Yeah, there is a video tutorial in Moodle. It's under the mastering module. So there actually is a tutorial for chapter 3 and a tutorial all about just ChemDraw. So I kind of go through and give you an example. Here's how you got to do it. Put all of your atoms down. Now click on the bond. Now click and drag to form bonds between the atoms you want to. And that way you kind of control how you make the bonds. So that's like one that challenges, but once you do it that way, then you're like, oh, that's not very hard. Why did I think this was impossible? So hopefully that helps a little bit. I'll just tell you. All right. So if you didn't get a functional group handout, that is the small little card or the small little laminated card that I've got up here. Okay. So this, you may want to grab one. I hope I have enough of them. I think I do. People have to swipe them and don't come back with them. Functional groups, these are groups of atoms that you might find in an organic molecule that are not just hydrogen. Some of them we've actually already talked about. For example, and I don't like this one, this one. Where are you? So for example, we talked about molecules that are nothing but single carbon to carbon bonds, right? So this is like pentane. 1, 2, 3, 4, 5. One's on each end. So that A and E on the end actually tells you that all the bonds between the carbons are single. There are occasions where you might see a double bond, and I kind of mentioned this and told you they're saturated as all the single bonds. Double bonds can exist. If you look on your card, see in the upper right or upper left corner, You have the alkanes, which is listed like carbon, 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 but all single bonds. The alkenes have that double bond to them. The alkynes have a triple bond. So this is that YNE ending. Those have a triple bond. You don't have to worry about naming these. So we're not going to like name a molecule that has an alkyne. We're not going to name a molecule that has an alkene. All you have to do is just identify the double bond would belong to the group that is considered an alkene. A triple bond in a between two carbons would put it in the group of being an alkyne. And you have this when you take your exam, okay? So you get this too, so you don't have to like memorize them. Again, this is kind of like a periodic table. So this one is really like, I want you to be able to use this. This handout is also posted in Moodle, okay? So if you want like a physical copy of it, you can print this to be able to use. So we have alkanes, alkenes, and alkynes, right? So those are single carbon to carbon bonds, carbon double bond. A carbon double bond to a carbon is an alkene. A carbon triple bonded to a carbon is an alkyne. The fourth one, you can see in this upper right-hand corner, that is the aromatic. So when you look at this one, do you see how it kind of looks like a combination? It's a ring. It looks like a cyclohexane. But you notice that the bonds are a single bond, double bond, single bond, double bond. So that arrangement, and it might actually, this is the skeletal structure like benzene is. You might also see it so that the bonds are on like the opposites. So they might be that where the bonds are this way. Sometimes it might look like the bonds are this way. Either one, it's the same because remember these things can rotate around. They're not like stuck in position. Double bonds and triple bonds are actually pretty reactive. They tend to form molecules that like to react with other things. Like nitroglycerin, TNT, has like 5 double bonds in it. And that's part of the reason that it's explosively reactive is because of all those double bonds. But when you have a bond where it's like this, where we have this ring, and it's single, double, single, double, single, double, they actually like stabilize each other. You will sometimes see this drawn where the alternating single and double bonds look kind of like the cyclohexane, and they'll put a circle in the middle. So don't let that throw you if you see it. I try not to draw them that way, but sometimes they'll put them in like formulas that way. So if you see this like hexagon with this ring inside, that's the same thing. Yes, it'll always be 6-sided. Yep, because a 5-sided can't have alternating single and double bonds. Okay, so it'll always be 6-sided and it'll always have alternating single and double bonds. Okay, so that's the fourth one. So those ones are really just carbon, just different arrangement of carbon. We can have carbon with just single bonds. Those are alkanes. If there's even one double bond between carbons, that's an alkene. A tripled bond between carbons makes an alkyne. And if you see a 6-membered ring with alternating single bonds and double bonds, they call that an aromatic. They named them aromatic, like benzene is like one of those like solvents, and so it's kind of smelly. So it sort of got these names because they were sort of aromatic or smelly kind of compounds. So like that. So you might see that like 6-membered ring with like the circle inside. Sometimes you'll see it drawn like that. I actually prefer to just draw them like this, just because I think it's like pretty clear that it's the aromatic shape. So notice that if it'll let me, it always lets me blow it up unless I want it to blow up, and then it doesn't. So notice in the, see. Okay, so notice in this, like, so there's morphine, there's oxycodone, there's tramadol, naloxone, all in this. These are all the opiate pain reliever types. So notice those ring shapes. A lot of them will end up having multiple rings all grouped together. A lot of similarity in them. And also that shape is the reason that they have their function. So their chemical shape is adding to their function, all giving them that function of having that pain reliever, analgesic type of function. Okay, so we got through these ones. So we have alkanes, alkenes, alkynes, and aromatics. These ones are just between carbons. But now, organic molecules like carbohydrates, lipids, proteins, they don't just specifically are carbon and hydrogen. Most of these are your fuels, your gasolines, things that are lipids. When we start to add oxygen, remember that's part of CHM, carbon, hydrogen, oxygen, nitrogen. So oxygen is a very common atom that you find in an organic molecule. They don't make up the majority of it, but you find them scattered throughout many organic molecules. And so depending on how they're arranged, they have a specific functional group name. So again, you don't have to memorize them because they're right here. Okay, you'll have this for your test, so you don't need to put it on your study sheet or on your note card. Instead, it's just a matter of trying to recognize, writing down notes about how can I pick out an alcohol. Okay, how am I going to recognize an alcohol if I see it on a molecule? So the ethanol is the example. So that is ethanol, which is like grain alcohol. So that's like what's in beer and wine. CH3, CH2, OH. So having nothing but an OH, an alcohol connected to a hydrogen on a carbon that has nothing else on it, nothing else connected to it except other carbons and hydrogen, that is an alcohol group. So we can have methanol, that would be a single carbon. We can have ethanol, which would be a 2-carbon group. You can have propanol, which would be a 3-carbon group. Okay? We're not going to worry about trying to actually name these. All I want you to be able to do is if you see this, you need to be able to tell me that's an alcohol group. Okay? So you see the alcohol group that's listed on your chart. Notice it's just a carbon with an OH on it, which means there's no nitrogen, no other oxygens on that carbon. It's nothing but carbon and hydrogen on that end carbon, and the alcohol's hanging off. So the alcohol can be on the end, but I could have an alcohol because someone asked this last night, and I was like, well, maybe I wasn't. So I could have an alcohol like this. So do you notice in this, the carbon it's connected to is just connected to other carbons, okay? There's no other oxygens around. There's no nitrogens like connected to any adjacent ones. So that's why this makes this just an alcohol. So an aldehyde, when you look at the way an alcohol is written as a condensed structural formula, CH3, CH2, OH, which means a carbon with 3 hydrogens, right? So that's CH3, means carbon with 3 hydrogens. Then I see CH2, which tells me that's connected to a carbon with 2 hydrogens. Then I see OH, which means then I have an oxygen connected to a hydrogen. So you've got to remember again, oxygen never has more than 2 covalent bonds. So oxygen's always going to have 2 dashes connected to it because it's got those non-bonding electrons. Carbon's always going to have 4. So you're always going to expect carbon to have something up, down, left, and right? 4 lines connected to it. So that condensed structural formula tells you how ethanol is arranged. But look at the aldehyde. So this is ethanaldehyde. So this is CH3, CH2, and then there's a C, and then how many hydrogens attached? 1. So CO, it's CH, so that tells me there's a carbon with 1 hydrogen. But then I have just an O. Well, how many bonds does carbon need? How many bonds does oxygen need? Okay, so how is this going to be connected? This will be a double bond. So do you see by making this a double bond, that gives me the 4? Carbon now has 4 bonds. Oxygen only has 2. Oxygen will never have more than 2 in our class. So that's the aldehyde. Now aldehydes, I can tell you, are always on the end of a chain. They will never be in the middle. So see how like that alcohol up here, how it's like sticking off of the middle of the chain of carbons? Alcohols could be on the end or in the middle. You just don't know. That one's not specific. But I can tell you that always aldehydes are on the end of a chain. So you're going to have carbon, carbon, and then an aldehyde. So it's never going to be in like the middle of a chain. It'll always be on an end. And it's always when you have a double bond to oxygen and a hydrogen. Okay, so like formaldehyde was our simplest one, example of that one. Remember, that was just that single carbon with the double bond oxygen, 2 hydrogens. That's an aldehyde. So now, if the alcohol and the aldehyde got together and had a kid, I guess, then they would make the carboxylic acid. Because doesn't a carboxylic acid look like an alcohol with an aldehyde together on an end? So think about it as being these two together made this different group with a new function or a new characteristic. So I have CH3, so that means that I have a carbon with 3 hydrogens. And then I have COOH. So that means this carbon's going to have an oxygen, and then there's an oxygen with a hydrogen. So that condensed structure, it's telling me that there is this hanging, or sorry, it's on the other one, back up one. So this is the CH3, and then there's another carbon with a C double bond O and an OH. That's a carboxylic acid. So if you break this up, carbox, then ilic, okay, into the name, because that one like throws everybody trying to say it. Vinegar is a carboxylic acid. It's acetic acid, but this is what that actually is. So it's just an example. We could have a really long chain, but the carboxylic acid is like an aldehyde. It'll always be on the end. Okay, so you're never going to see it like in the middle of a chain because on the end is the double bond oxygen and the alcohol. So that means that that carbon is only ever attached to one other thing. Okay, so alcohol, aldehydes, and carboxylic acids, these are where you have combinations of carbon with oxygens. If there's a nitrogen, it's one of these. So if you're looking in a molecule and you see a nitrogen, you know it's an amine or an amide. It can't be anything else. Okay, so these are the only two, and you can see those ones. I have the alcohol, aldehyde, and carboxylic acid sort of at the top of your little group. Then notice in the bottom left, the amines and the amides. Amines and amides always have nitrogen. An amine just is a nitrogen attached to a carbon, but there's no oxygens attached to it. So if you have a nitrogen, I could have a nitrogen in the middle. I could have a nitrogen on the end. It really doesn't matter. I could have a nitrogen attached to 3 carbons, but there's no oxygens attached to any of the carbons that the nitrogen's attached to. That's kind of the key thing. Then it's an amine. But if you see, and I don't really like I won't draw one that looks like that. If you see one that is like CH3, no. Okay, back. I'm like, geez. All right, so if you see one, I can't put an H down there or it's going to do like, it'll put me into subtitles or something. So there's an H down underneath. I just can't draw it. Then I have a CH2, so there's a C, and there's an H, can't do it. But here, so if there is a carbon with the double bond oxygen attached to a nitrogen, and in this one, it's attached to, this nitrogen has a hydrogen, 2 hydrogens, and then 3 hydrogens on the end. So that is the shape that you will see for an amide. So you will see this. So when you look for, if you see a nitrogen, look at any carbons the nitrogen's attached to. If any of those carbons have a double bond to oxygen, that's an amide. This is how proteins are put together. Peptide bonds are held together by bonds that are called amide bonds. Okay? So that's like they're significant. We will talk about them again when we talk about proteins. But notice that difference from the amine. So the amine might have lots of carbons attached to the nitrogen. So I could have CH3 to a nitrogen and a CH3 and a CH3. But that's still an amine because none of those carbons have double bond oxygens. So when you see a nitrogen, just look at each carbon that it's attached to. If there's no oxygens around, then you're good. It's an amine. If you see a double bond oxygen on any of the adjacent carbons, that's an amide. Okay, last ones. Okay, so ketones are when you have that double bond oxygen, but it's in the middle of a chain. Acetone is an example of this. So acetone, which is like nail polish remover, this has this ketone structure. So I could have a long chain of carbon, but if one of the middle carbons has a double bond oxygen hanging off, then that's a ketone. Notice there's nothing else around it. Ethers. Ethers were early anesthetics. So they would actually distill, so you could make, ferment corn mash, and so that's like how you would make like moonshine. But so some of the byproducts in that mash would actually be ethers. Well, when you go to make your moonshine, you boil this off. This boils off really quickly, so it doesn't end up being collected. But what they would do is they would actually collect this. You could put the ether, it was a gas, so they would put a small amount in a mask and put it on your face and knock you right out so they could do surgery. So this were some of the very early anesthetics were ethers. Problem is they're extremely flammable. Okay, extremely flammable. And so that's not always so good if you're working in a surgery suite where they have to actually cauterize things where you might have a spark because things blow up kind of thing because this is a gas. So those were very early anesthetics. Not so much in use now. Okay, now they're all chemical type of anesthetics to knock you out. Nothing like some propofol. All right, so ethers, though, notice the difference between a ketone and an ether. So a ketone is when you have a double bond oxygen hanging off of a chain. An ether is actually part of the chain. So if you have carbon, 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 oxygen, carbon, 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 that is considered an ether group. Sort of like the alcohol and the aldehyde on the previous page, if you take a ketone and an ether and put them together, that makes an ester. So if you ever see an oxygen in the chain, so if you see an oxygen and it looks like it's spanning two carbons with single bonds, then you just want to look to see, is there a double bond oxygen anywhere? Is there a double bond oxygen connected to either of the carbons on either side? If it is, then it's an ester. If it's not, then it's an ether. Esters are pretty interesting because these are all your fruit flavoring, so bananas, mints, apples, peaches, the ripening, when you smell a fresh fruit. Most of the time those are esters. Thiols are pretty easy. Anytime you see a thiol, no matter what it's attached to, just call it a thiol. Okay, so the thiol this sulfur might have oxygens on it. I don't care. It's a thiol. It might be two sulfurs linked side by side. I don't care. It's a thiol. Okay, they do have special names. We're just going to name them all thiols. Okay, so example thiols are all that swampy, eggy kind of smell. Those are very characteristic. So if you've ever boiled eggs and forgot and boiled them way too long and you peel them and slice them, what does the yolk look like? Green. Okay, the outside of the yolk gets really green. Have you ever seen that? Okay, well, maybe you've never made eggs. So the reason for that is actually because there is a lot of sulfur-containing amino acids in egg whites. They're almost all protein. And so when you boil them too long, those amino acids break down and actually form a little hydrogen sulfide ring. And that's why when you open the egg, you're like, oh, God. You can smell that eggy smell. But if you boil an egg so that it's just done, you will get no green ring, and you should not notice that strong odor. Okay, the longer egg salad sits, the stronger the smell gets, just because the amino acids just start breaking down automatically in the egg whites. But overboiling your eggs will cause that to happen a lot faster. So I was we used to have egg salad sometimes for lunch when we were kids, and it was you'd sit down and open your sandwich, and everybody would move away from you. You're Dad, don't send me egg salad anymore. Okay, just remember, if you see a sulfur, it's just a thiol. Okay, I don't care what it's attached to, it's a thiol. Okay, so now the last one. So you see the thiol on there. Last one, down in the bottom right corner. This is a phenol. This looks like a what? The ring looks like the aromatics. So notice the similarity. Six-membered ring, alternating single and double bonds. But it's not just an aromatic. It's got that OH group on it as well. So it's like an aromatic and an alcohol together. So I wouldn't name it as an aromatic. I wouldn't name the alcohol. I would name the entire group as a phenol. Phenols themselves have different characteristics than aromatics do. They have different characteristics than alcohols do. That combination gives them sort of a new job. So one example is phenol was one of the very first disinfectants. So 200 years ago, it was very common for women when they went into labor, they would go to the hospital and the doctor would deliver the child. A lot of times they use forceps, they use all kinds of craziness. And the doctor would literally go from one mother to the next, to the next, to the next, all day long. Okay? Not washing hands in between, because that wasn't truly understood back then. And a lot of women died of childbed fever, okay? Which just meant after they would end up developing a uterine infection because one mother came in and she had something. Well, the doctor didn't wash his hands, so then he passed it to the next mother, the next mother, the next mother. Mm-hmm. And so somebody was like, why is this happening? And why does it seem like it's in runs? Like, all these women will end up dying, and then we won't have a problem for a while. And then all these women end up dying. And so they were like, So they actually started having doctors dip their hands in phenol. So phenol was really, so they would just keep a basin of it. It's kind of stinky because it's a disinfectant. It's almost like Lysol. But they would actually dip their hands a couple of times instead of washing with soap and water, like God forbid, okay? But they would do that, and they found that these infections dropped dramatically. So that also helped them to understand a little more about aseptic technique, little understanding. That's when people started getting into the, well, we should boil stuff, right? Because if we boil things, the things seem to be cleaner. Like we end up with less of these infections. So it helped to lead to all of the sterilization and the processing that prior to they really didn't even understand. In fact, at one time, there was somebody whose job in a surgery suite, their job, they had a mister. So I always think of like perfume, you know, like their job was to like stand in the surgery suite and mist the patient with phenol. Okay? They didn't understand about a betadine scrub, right? They didn't really understand about gowning and trying to cover all areas except what you were doing surgery on. Instead, they had some guy standing over here like misting the person with Lysol, which I guess is probably because disinfectants, just as a note to self, disinfectants are really not meant to use on living surfaces. Disinfectants are for non-living surfaces. Antiseptics are what you use on living surfaces. So phenol can be a bit strong to be used as something to clean the skin, but it was kind of like this beginning of this understanding that we need to use something that chemically is reactive enough to be able to reduce microbes on surfaces. So that's a phenol. So if you see this ring, the trick is if you see a six-membered ring alternating single and double bonds, it's either an aromatic or a phenol. Okay, so all you want to do is look at all the corners of the ring and look for an OH. If you see an OH, then you know it's a phenol. If you don't see the OH, then you know that it's an aromatic. Okay, so now using this, look at aspirin. So aspirin is the upper left. You tell me, look at your picture and look at this and tell me one thing you see in this molecule. There's three. There's a carboxylic acid. Does everybody see this one? So the carboxylic acid, remember I said it's always on an end. Carboxylic acid is when you're going to have a double bond oxygen and an OH on the end of the chain. There's an ester. Yeah, that's good. That one sometimes is hard. So see this? Okay, it kind of looks like a carboxylic acid, but it's always in the middle. So the ester is always going to have carbons on either side, where you have an oxygen in the chain and a double bond oxygen on an adjacent carbon. One more. An aromatic. So everybody see the six-membered ring? Sometimes the way they draw these rings, notice like that upper right double bond is kind of odd. It's not like in, it looks like it's outside. It's still double bond, single bond, double bond, single bond, double bond, single bond. So this is an aromatic. All right, look at Tylenol. What do you see? Yay. Right? So you found the ring, and then you just check to look for an alcohol. So if you see an OH, then you know that this is a phenol, not an aromatic. See the difference between the two. They both have that ring, but one has an OH, the other one does not. One more thing. There is this double bond, but remember, always look, what do you see on either side? What does that make this? This is an amide. Okay? So you see that double bond oxygen, just make sure that you look at the carbons on like the adjacent carbons to what it's attached to. So that is an amide. Look at your card, see if you can kind of like rectify how that looks like what you see on that card. All right, go down to Advil, ibuprofen. What do you see? A carboxylic acid, box, and then ilic acid. One more thing, aromatic. Right, so there's the ring, but no OH, so that makes this an aromatic. What about saccharin? 3 things. Yep, there's an amide. So you see the nitrogen. Remember, if you see a nitrogen, always look to see is there a double bond oxygen on an adjacent, so that's an amide. Then, what else? Aromatic. And that's, again, kind of a weird-looking 6-membered ring, but if you look, it's a single bond, double bond, single bond, double bond. And the last thing is a thiol. I don't really care that the oxygens are attached to it. We're just going to go with it's a thiol. Anytime you see a sulfur, it's a thiol. So the last one's some Valium. All right, what do you see on the Valium? This one's like a real skeletal structure. There's an amide. See it there? Okay. What's the other one? That's an amine. This is an amide. See the difference? So the top nitrogen has a carbon with the double bond oxygen. The bottom nitrogen does not. Neither of the carbons on either side have anything. So that's the difference between the amide and the amide. And then the last 2 things are both aromatics. Do you see 2 aromatics? Okay. Here and here, these are both aromatics. All right, so this isn't really a molecule. I just made this up. Okay, but there's 9 functional groups in this molecule. Okay, so see how many you can find. Okay, so I'll give you a minute. See how many of them you can find. Like count to yourself as you see them, and then we'll go through, circle them, and label them. Okay. So my suggestion is like look for rings, because those are aromatics or phenols. Look for nitrogens, those are amines and amides. Then you can look for the oxygens, because those there's more possibilities. Find those, identify them. Okay, so tell me one. Where? Right in the middle. Okay, did everybody catch this one? Right, so this is a phenol, not an alcohol. So look for the rings. Like I would say, if you get a structure, look for the rings first. Those are either aromatics or phenols. Okay, look for the nitrogens next. Those are amines or amides. Okay, if you see any S's, those are thiols, because those ones you just move. That's the only thing they can be. Then do the oxygen comparisons. Okay, tell me one more. Okay, I heard aromatic. Everybody see how this is different from the phenol? Okay, what's another one? An ester. Where's the ester? What do you mean beginning? Upper what? This is an ester. Right, so ester's in the middle of a chain. Ester will always have carbon, oxygen, carbon, and one of the carbons will have a double bond. Okay, what else? Where? Coming down off of the phenol, do you see the amide? Right, you found the nitrogen. Since there's a double bond oxygen on the adjacent carbon, it's an amide. What else? Ketone, where? There's only one, but where is it? Between what? Between the ester and the phenol, okay? So see how that's just in the middle of the chain, that double bond oxygen. Neither of those carbons have anything fancy on them, so this is a ketone. So which other one did you think was a ketone? Okay, so what is that? An aldehyde, right? Remember, aldehydes are on the end. So aldehydes will have a double bond oxygen, but then a hydrogen, because they're always on an end. Ketones are always in the middle. They look a lot alike, but that's really how you can tell them apart. So this is the aldehyde. Yep, the carboxylic acid, the one everybody likes to say, not. Carboxylic. So it's a carboxylic acid. One more. Thiol, yep. And there's an amine. Okay? So you see in those? Yeah, there's all 9. Okay? All right, well, I'm going to have to stop and like go back to it because it won't let me change colors again. And then I have to reconnect. So that's my life. So practice these. Here's this one. I made this with ChemDraw. Okay. So this one's in there. So you tell me, what do you see? What's a quick one? Thiol, right? Does everybody, first one you should pick out, right? Because the first one, if you see an S, it's a thiol. You don't have to even like wonder which one it might be. Okay. I also heard someone say there's a aromatic where? On the bottom left, bottom right. Both, right? Do you see that both of those are aromatics? Okay. And the what? So see the other aromatic, but see the alcohol group on it. So that is a phenol. So see, that helps to kind of like take some of these out, and then you're left with others. So now do you see any nitrogens? So is it an amine or an amide? So do you see the amide here? Nitrogen with the double bond oxygen on that carbon, that's an amide. Do you see any other nitrogens? Look for an N. Just look for the N. Like if I was going to name these, the first thing I would look for is look for the ring. That's either an aromatic or a phenol. And that once you've named those, you're not going to name them again. So like the phenol is not going to be an alcohol too. The phenol is a phenol. And that takes care of the ring and that OH. Then I would look for, then I would look for nitrogens. Okay, just kind of scan the molecule, look for nitrogens, because you know those are amines or amides. Okay, and so then once you circle the nitrogen and its double bond oxygen next to it, then now those are gone. So I'm not going to name those anymore. So you kind of just go through and you're picking anything that's not just carbon and hydrogen. Say the what? Find an NO by itself. Do you see that? Do you see this N? You look at the ones on either side. Do you see either of the carbons attached have a double bond oxygen? No, it's an amine. Because here's the nitrogen connected to a carbon with the double bond oxygen. An amide. Oh, I wrote it wrong. Yes, thank you for catching that. No, I can't erase it unless I go back. There. Sorry. I meant to write amide and I wrote amine. It is an amide. You're right. Yes. So that's, so look at for the ring. Those are aromatics or those are phenols. Look for nitrogens. Nitrogens are amides or amides. Okay? Now go and look at the rest. So all the rest that are different, there isn't a file, is there? We named the file already. So those ones are pretty much like, you can circle those and get those like out of the way. Now you look at the remaining ones and pretty much those are always oxygen. So find an oxygen. What is that one on the end called? That is an aldehyde. An aldehyde is a carbon with a double bond oxygen, and it's on the end of the chain. Do you see any other oxygens next to the amine? So what is that called? That's an ether. Ether, ether, fine. You pronounce it however you pronounce it so that you can spell it, right? To help you in the spelling. Okay? But you will have this. Okay? So just reiterate, you will have this. So you will have something to look at, something to refer to when you take your exam. So you don't have to like memorize what their names are. I just want you, like, you want to practice this, practice identification using the little card. All right? So guess what? There's another one. But I'm going to leave this till next time. Okay? So this leads us into the last grouping about isomers. So isomers we've talked about in labs. If you're in the lab class, we've really covered that. The term iso means the same, right? Like isotonic is the same salt. So that's an equal balanced salt. Well, isomer just means that it's the same group. Isomers by definition have the same molecular formula. That means that they have the same number of carbons and hydrogens. And no, I'm not going to ask you isomers for any of the functional groups. It would only be isomers of just the basic carbon, hydrogen, halogen ones we've been naming. So you can have isomers that either are differently arranged or look differently arranged. So if they are differently arranged, then they have the same formula. C4H10 is a good example. 4 carbons, 10 hydrogens. See, in this first example, there are 4 carbons in a row. So you would call this what? Butane, right? So this is just butane, 4 carbons in a row. But see, the one that's next to it also has 4 carbons and 10 hydrogens, but the 4 carbons are not in a row. So I have 3 carbons in a row, and then I have this group that's hanging off. So this one, what would its name be? Longest carbon chain would be a 3 carbons would make propane. The single carbon group, CH3 hanging off, is a methyl group. And it's hanging off of the middle carbon, so that would be number 2. So do you see that those have the same number of carbons, the same number of hydrogens, but they don't have the same name because they're not put together the same? Those are structural isomers. And really the way you know is you just name them. Okay? So that's where understanding and being able to do the name consistently is helpful in trying to identify which ones these are. But then if I look at the group over on the right, so again, 4 carbons in a row, you see that this is also butane. The carbon group on the right side of it has 3 carbons in a row, but one group sticks up off of the end. So how many in the longest chain? Do you see that this still is 4? It's drawn differently, but it still actually has 4. So this is also butane. So they're both the same, but they look different. So if you remember, we called it like the straight and the bent. Okay? Remember, with single bonds, they rotate. So they're not like stuck in position. I could actually take this zigzag and like draw it this way. That would still be the same, right? It would be, I could do my zigzag this way or start and go up and then down and then up, either direction. In fact, I could draw butane. I could say that this is CH2, CH2, sorry, CH3, CH2, CH2, my pen's acting wonky, CH3. That's a CH3, CH2, CH2, CH3, so that they look vertical. It still would be butane. It's still 4 carbons in a row. So those are called conformational isomers. So structural isomers are molecules with the same number of atoms, but they're put together differently, and they have different names. Conformational isomers are drawn differently, but it's actually the same molecule. So they have the same connectivity, and so they're going to end up with the same name. So you tell me, 1, 2, 3, those 3, are those structural isomers or conformational isomers? They're all structural. And you can tell just from looking at how they're connected, yeah? So they're all 5 carbons, okay? They're all going to have 12 hydrogens. There's hydrogens above and below, hydrogens on the end, okay? So 5 in a row, this is pentane. But the next one in the middle is only 4 in a row, so that makes this a butane. And then that CH3 group hanging off is a methyl. It's hanging off of carbon number 2. If it was hanging off of the end, then that would still be pentane, right? So if it's hanging off of the end, it's still part of the longest chain. But this one's hanging off of one of the interior carbons, so it's a methyl group. And then what about that last one? Do you see that still 5 carbons? When you count 1, 2, 3, 4, 5, there's still 5 carbons in that one that are on the far right, but only 3 in the longest chain. So that means this is a propane. This group is the one at the bottom is a methyl. So that means these two together are a dimethyl, and they're both off of carbon number 2. Okay, so you could put 2, or you could put 2, 2. Those are all structural isomers. Same number of atoms, but they're put together differently. They have different names. That's the easiest way to tell them apart, if they have different names. Or if you can actually tell. You could kind of look at these and tell. Okay? Can you tell with the bottom one? Structural or conformational? Why? What are their names? They're both butanes. Can you see that? Can you see 4 carbons in a row for the first one? For the second one, it goes over and then down. 4 carbons in a row, 4 carbons in a row. So they're both butane. Bromine's off of carbon what? 1. So this is, do you see this is going to be a 1 bromo? How about this one? It would be on carbon what? 1, right? Because I'd have to start numbering from that spot. Chlorine's is going to be on 3 because we go 1, 2, 3. So this would be a 3 chloro. And this one would be also a 3 chloro. So these ones are conformational. So sometimes you can look at them and tell. Sometimes it's a little harder to tell. Now, if you see one like this one, last one, and then I'll quit. If you see this one, how many carbons in the first one? So total of 8, okay? And then there's a bromine, right? So do you see 1, 2, 3, 4, 5, 6, 7? So it is a heptane. So the longest, it is a heptane. And I do see that it's C8. What about the one on the other side? The longest carbon chain is a hexane. Does everybody see that? But how many carbons? Count all total. Do you see that there's 9? You would say these are not related. They do not have the same formula. Okay? So this is one of the big things to do, if I could spell. Not hot, not. Okay? They're not related. So if they don't have the same number of carbons, or if like one had a bromine, one had an iodine, then you can just go, these are not related. You don't have to worry about naming them. So kind of like go through and count. Don't worry so much about the number of hydrogens because those will always fit themselves in. But if the number of carbon atoms are different, or if there's a group like a chlorine, bromine, iodine, fluorine, on one and not on the other, then you really don't even have to go any further. You would just say they're not related. Okay, so put yourself a note. To be an isomer, it has to have the same molecular formula, the same total number of atoms in each molecule. Okay, so I'm going to quit there. There is 1, 2. There's this one. We'll do this one first thing. We'll do this one. And then we can go on and talk about the stereoisomers and finish this on Tuesday. If you didn't pick up your exam, I have them.